Good morning, everyone. So my name is Jaru. I'm currently a postdoc working in the Matter Lab under supervision of Professor Speculic. So today I'm delighted to start the first AC sampler session of the term. And it's a special honor for me also to introduce today's speaker, Professor Markus Kraft, my PhD supervisor. Professor Kraft is from Cambridge, Department of Chemical Engineering and Biotechnology. And he was also the founding director of the Cambridge Center for Advanced Research and Education in Singapore. And he has been in Singapore for 13 years from now, basically covered the entire period of my PhD. And this year he's a visiting scholar, visiting professor at the MIT. Professor Kraft is internationally recognized for his pioneer work in combustion, reaction engineering, and the carbon reduction technologies, all of which were before I joined the group. And now he's more known for his new baby, the World Avatar project. And today he will be sharing us how he used the World Avatar in material discovery. So without further ado, I guess.
Well, Jaru, let me just continue a little bit. I'm very privileged that Jaru came to University of Toronto as a Schmidt postdoctoral fellow, coming from Markus Group, and connected us and the Acceleration Consortium to him. He has the prize of the best dressed speaker ever in our seminar series. So, that deserves a present from the Acceleration Consortium. Okay, so I want to just welcome Professor Kraft. We really have learned a lot from his research in knowledge graphs, and really has transformed the way we do research at the Matter Lab. Thanks to Jaru as a bridge. And we're going to give him a few presents that I know he hopefully are going to bring back on like this. A pin of the Acceleration Consortium, this fits in your pocket, right? A notepad that is green and renewable, and then a cutting board. That's
sorry, a what?
A cutting board.
A cutting board.
Made of Canadian. Okay. And some stickers of Steph Driving Lab. So I just want to give you this and welcome you to the University of Toronto.
Thank you.
And then I'll just put it here for you. Okay.
Okay.
So
thank you. Thank you. Well, I'm very glad to be here. And in fact, it's the first time for me to be in Toronto. Just to give a bit more information about me, I'm from Germany. I grew up in the most beautiful part of Germany. No, not Bavaria. It's Palatinate. It's I'm not sure how much you know about Germany and France. It's north of Alsace, at the border between Lorraine and Alsace. So this is where I grew up and studied mathematics, and then later did a PhD in technical chemistry. And then I spent 2 nice years in Berlin. And 1990, I moved as a lecturer to Cambridge. And I was there until 2013, where I started my position as director of this research institute in Singapore. And after 12 years, I stopped it and had the opportunity to go to MIT, working in Bill Green's group, and with Connor Cooley, whom you may know because they also do material discovery and machine learning. And then after this, I'll go back to England. So maybe a short remark about my bow tie. These are, of course, the colors are catastrophe, right? You shouldn't wear this color combination. But the main reason I'm wearing it, this is my college colors. So I'm a fellow of Churchill College, and they chose this color combination. Okay. But you just have to carry it. Okay. So that's what I'm doing. So now you know where this interesting bow tie comes from. Okay, so let's get started. This project is about material discovery in the world avatar. What is the world avatar? It's crazy. Am I crazy, right? Yes, a little bit. Okay. The world is not, I mean, like an avatar, you saw the film, is sort of a representation of something. It comes from Indian mythology, and there's a big thing about it. I cannot tell you all the details, but what here means is a representation. And the world doesn't mean planet Earth. It means the world at large. And what does that mean? It's the, in a more mathematical sense, it's the set of all possible concepts and their relationships, right? So if you were to, if I ask anybody of you to describe what's happening in here, you would use your language and you would use words. Or if you were to say, describe who, I mean, like what you see, you'd probably say something, there is a speaker in front of me and is a human and so on, yeah? And in fact, these are all made up things. Okay, it's even difficult sometimes to really define what a human is. If you just look at the mass, you know, you think of yourself, you are the person, you've always been the person. But I argue this is actually not so trivial. If you just look at the molecules that constitute, that make you right now, in a month's time, 20, 30% of these molecules will have been exchanged. So you're not even the same person in terms of mass and molecules. You're basically like a stirred reactor. I mean, like a bit more detailed, okay? And so is your representation of things, okay? So what it really boils down to is information representation and doing this through concepts. And that is what the world avatar is. And there are reasons to go really big rather than just look at each problem in turn, okay? And we argue, if you want to really make progress with single use cases, you can only do it if you have a system that is able to represent any other use case. Okay, that is sort of the underlying hypothesis. Okay, let me, so what you see here, so now I'm moving into the realm of product design, synthesis, and lab automation, because that is stuff that's happening here. I would say if you work in this area, there's something called technology stack. This is all the things you can use. So you have databases, you use generative AI now, you have computational modeling that can be machine learning models, and you have robots moving around, automated experimentation. But they all need to be put together somehow, okay? And we call this knowledge engineering. That is taking information, putting them together, make things talk to one another, okay? So, and for us, knowledge engineering means ontology and knowledge graphs. What is a knowledge graph? How are we using them? In what other contexts are they used? Who knows in here what a knowledge graph is? Okay. So that means normally twice as many people know it. So I go very fast now, okay? Okay, knowledge graph versus standard databases. What's sort of the difference? Okay, this is basically for the MBA students amongst you, that Gartner Technology Review regards this as an important technology. And because it removes the barriers for AI implementation in terms of data accessibility, data volume and complexity, and hard to measure the value. Okay, so this is the value of things that are represented. I don't know whether you've seen this impact radar, but you can see here, okay, knowledge graph, we are in the middle of it. It's implemented. And companies like Google and Facebook, they're already doing this. So for example, in search engines, you'd find knowledge graphs, in AI assistants, healthcare, bio, enterprise knowledge management, and so on. So companies use elements of this. So what is it? Okay, so here is an example that we've been using in for my home city in Pirmasens. Okay, so you see here a building, and that has an address. Okay, and it is in a flat. So these nodes define entities and data. So if, for example, I'm an entity here, I'm a human, I'm a specific representation. Okay, the edges, they connect entities to concepts and to data. So for example, there is also a representation of human. Okay, and so there is, in a knowledge graph, there would be an edge from the representation, the concept of human, to me. Then, and the concepts I have just mentioned, and the concepts, these are defined in the ontology. Quick example. So you have T-box as a terminological box that gives you the schema and the ontology. And here's an example. Politician is a subclass of person. Okay. President is a subclass of politician, and then individuals, Barack Obama is a president, Honolulu is a city. So this is a typical triple representation. And I don't want to go into details. Another thing that is important to know, that these nodes and the edges, that this graph is represented in terms of IRIs, internationalized resource identifiers, basically web addresses. And that is a huge advantage, because it basically means that you can distribute it over the whole of the internet and every computer server that's connected to it, which basically means your resource is enormous, okay? Because every data center, every cloud is in principle now your resource, depending on what software they run. Okay, you can do inference. Okay, here, so for example, you know, politician is subclass of person, and you know Barack Obama is president. You know the president is a politician. Therefore, Barack Obama is a person. Now, this is important because this is explicit knowledge representation. It allows you formal reasoning. It is not just a probability. You know, the reasoning that comes out of the large language models, the super models, they all make mistakes. But here you can be, you have at least a chance to be precise. There are other downsides to it, but at least this is an area where you can make correct statements. So what is special? Graph structure is linked, ontologies, structure extensible, expressive, okay. Multiple views of data is possible, different data structures are permitted, and it's shared data. So this is beautiful, okay. Why is it useful in a lab context? So we have, for example, chemistry represented in here, PubChem, but this is currently growing. Then we can represent the lab notebook, and I will explain this a bit later, and of course the experiment. So, right, so now, is the world avatar a knowledge graph? Yes and no, okay? So what is also important, so far we have only talked about data and concepts, okay? But now, if you look at me and you specify what I am, you know, I have properties. We already know I'm a human, okay? I'm a lecturer in this room, and I have a position, okay? And if somebody asks you, where am I? You'd say he's about half a meter away from this desk, okay? So now I do this. I ask this question again. What do you say? Now I'm 4 meters away. That means in your knowledge representation, there must have been a process that updated this value somewhere in your brain. And this is called agent. Okay? So there was an agent that updated the representation and my properties. Now this agent, and this is where the world avatar is a bit different, is also semantically represented. By doing this, you get, for every change in your system, provenance. Okay? That means if anything changes all through a whole chain of agents, then you can exactly say what happened and why. And if you want uniqueness, and this is very important for model building and model discrimination, then this is a critical ingredient. Okay? So, and if you then think about what that really means, that means if you do all this and represent a system in that format, it's no different to what happens in your head. Because everybody in here has a world avatar in their head, a representation of the world that is a mix of implicit and explicit representation that is dynamic, okay, but is made of cells. And at the moment, this is super, biology is hard to beat, but the internet is also very big. The computational powers are very big. So the next question is, how can we represent this? How can we see it through? And my task over the last 10 years is to experiment and see how we can do it and grow it and develop the technologies, okay? And of course, embrace anything that's on the market, okay? Good. So this is, so we have already made minor progress. So we have representation of the United Kingdom. We, for example, have a big infrastructure project where we actually work with Anglian Water. This is a water company, the UK Power Grid, and British Telecom in King's Lynn. And King's Lynn lies in Norfolk. I don't know whether you know where that is, but it's basically flat, okay? And if there is high tide, a storm, and sea levels rising, then of course the water goes into King's Lynn and floods. So what they want to know is, if there is a substation, how does that substation, the fault of this substation, traverse through the other infrastructure, say telecom or water, you know, because the pumps are all electric. If this substation goes out, where don't we have water? Who doesn't have access to hospitals and things like that? So we work with real data, and each of these companies is super digitalized. They have everything digital, but they can't talk to one another. So we are in the business, and that's the practical purpose, to interconnect. Okay, you can think of what we do basically like putting Lego wrappers around things so that you can stick them together. Okay. Okay, and then in my hometown, this happened during COVID. My mom turned 80, so I went from actually from Beijing, and there was this news in Beijing. Yeah, something in Wuhan. We don't know what it is, you know. And I thought, oh yeah. So I flew over to Germany to my mom's 80th birthday, and then I used the opportunity to go to TU Munich, and then somebody at TU Munich said, I think there is somebody who has this disease from Wuhan. And then I thought, And then I went back to Pirmasens, the southwest of Germany, and spent another couple of days. And then I want to go back on the plane, and everything was stopped. Okay, classical COVID. I'm sure everybody has their COVID story. That is mine. Okay, and then I lived with my mom for 3 months, which was a real interesting and nice experience. Okay, the good thing is we are both still alive, so we managed to get through. And so while I was there, then I thought, okay, we do all this digitalization in Singapore. So I went and saw the mayor of the city, and then it ended up with talking to the Stadtwerke, and then we completely build a representation of the city that also controlled the distributed heat network. So that was interesting. And then in Singapore, I've just mentioned it, we have a representation. This is used for various aspects for health, and we work with the company to organize the rubbish. And then and now we're going into buildings. So we have learned how to represent buildings. Some of you may know what a building information model is. And so we have ontologized that. And because a lab is in a building and there are aspects in the lab, like the fume hoods, the building management system, that have direct impact on the experiments, we thought, okay, let's try to look at lab automation holistically, take everything into account. Some of the mass some of the instruments, analytical instruments, for example, need to know humidity, they need to know the temperature. And now our digital twin of that machine can talk to the building management system directly, no need. And the machine can talk to PubChem and can basically look at its quantum calculation and do the interpretation of the spectra all in one go. Okay, so this is lab, and I've just mentioned it. We also try to go with this representation down to quantum chemistry representation. This is all work in progress, but here you can see the world really means anything, really. So time, 15 minutes, 20 minutes, oh God. So I want to say something, I want to show that this explicit knowledge representation can be useful to find new molecules. So the use of machine learning for material discovery, I would say, has been a triumph. There is no other way of saying it. And that's great. The use of large language models, also super. But they cannot do everything. You get a lot of hallucination, incorrectness, and so on. And if the molecules are very big, like in reticular chemistry, then it is not straightforward to develop machine learning algorithms, in particular when there is not enough data, okay? So what is reticular chemistry? Who knows what reticular chemistry is? Okay, few, okay, good. Right, so I'll be fast here. So let me just, they're important for a number of applications. They are basically, there are structures that are called metal organic frameworks. These are the most famous ones, I would say. These are 3D network structures, and they are periodic. And the non-periodic version is called metal organic polyhedral. They are non-periodic, there's a sort of 0D structure. And this is what they look like. This is an example. And they have building units. So now we are Lego. We can do the Lego again. So there is metal build, so this is called secondary building units, and this metal-based and organic. So, so these molecules, you could almost imagine to have it as a toy play set that you stick together. And they look like ideal Greek volumes, in this case, polyhedron, okay? And for example, this is how you can represent a Platonic solid, okay? It has faces, vertices, edges, dihedral angle, and so on. And the key point here is that you now use, I earlier explained how important concepts are. Now you have something that allows you to talk about a molecule in more ways than just a chemical bond, right? Now we can describe this big thing on a different level. And because we can do that, we can use that to do the material synthesis and discovery, okay? So if you want to discover material and to want to make it, then you have to go through different steps, okay? And ideally, you want to make a material that matters, something that is better than all the other materials you have. So how do you do this, okay? So the idea here is we start with a rational design, okay? So you make something up, and we have now the concepts to do that, okay? Then we do some structural modeling. We try to put it together somehow, okay? You can ask Jaru how to do this, okay? And then you, of course, you can build in Lego, but you still don't know, is that now right or not? So you want to then have a better understanding, and this is where the quantum chemistry kicks in and sees, can we get a converged solution of these molecules? What energy does it have, and so on. And of course, you also want to know, has it interesting properties? Because if it doesn't, then no, who cares, right? And but then you have to synthesize it. It's not enough to know, okay, this would be a good molecule. You have to make it. So the question is, how do you make it? Okay, how do you do that? Okay, and then finally, you want to check, is this really the thing I anticipated? So, and what I'm trying to tell you is that this can be all done, the whole workflow can be done within the world avatar context, okay? Right, so I'll go a bit, what does the time say? Okay. Right, I can slow down now a little bit. Good, so this is a classic metal organic polyhedral. So now I try to explain how we use concept and explicit knowledge representation to make up stuff. Okay, so the first thing is that we have to get the equivalent of the Lego set. Okay, so you have this metal organic polyhedral, and then you have these chemical building units. So this is a linker, okay, this is an edge, and this is a vertex. So you then say, okay, this is where you go from Markus to human. Okay, this is an instance of something more general, and in this case, it's a generic building unit, and it's just, we call it two linear. It's a stick. And here, this one is 5 pyramidal. So then we need to know, I'm sure you, who has bought stuff from IKEA here? Okay, okay. This here, this is called assembly model. This is the thing that says there are n+1 screws in the box, and you can only find n. Okay, this is the so this is the assembly model. This tells you how to use the generic building units and stick them together. Okay, right, excellent. Now in mathematics, you could say a generic building unit acts as an equivalence class. Okay, an equivalence class. This is a class where the members, is a set where the members of the set have a common feature. Okay, so for example, divided by 4 with rest 3. This is a classical mathematical equivalence class. So these things form equivalence classes, and the set in these classes contain chemical building units. So the question is, where do you get these from? Where do you get these building units from? So what you do then is you go through the literature, right? And my postdoc, Alexander Kondinsky, who is now assistant professor in Graz, he did proper hardcore science. So he went through all these molecular structures and extracted the assembly model, first of all, the shape, and the different assembly models accordingly for a given set of general building units. And from those, we could identify, these were derived from metal organic polyhedrals that were found in literature. Okay? And that meant, okay, so, and that meant that we could now, for each of these, come up with an occurrence class, a set of molecules. And then the only need to, so we used basically this pyramidal structure, and then it has these edges, and then these edges could be one out of this set of molecules. And all you need to do is then to combine them, you know, and that creates a much, much larger set than what has been reported in literature. And this is how we find new structures. So, and here you see a little bit of an ontology ontology example. So, for example, here is the metal organic polyhedral. This has a formula, has an assembly model, polyhedral shape, has a chemical building unit, has a geometry, has a molecular weight and charge and so on. And you see that this representation is made of several ontologies. These ontologies are not static, they change. And then we had 137 instances from the literature and 7 generic building units, and we were able to find in total 1,418. And now we are just in the process of taking these linear building units apart and in turn turn them into Lego 2. And so you can easily extend this to several tens of thousands. Okay, and each of those molecules needs to be looked at. In the so now we have proposed, okay, here is, you know, there's a difference to getting the stuff from IKEA and having the assembly brand. That doesn't necessarily mean there is a shelf at the wall in half an hour. Okay, so so we now need to go from the delivery and the building plan to the shelf that we want to build. So we need to build it. Okay, and that doesn't always work. So let's build it. So here, construction target input data. So the packet has arrived. Okay, now we look at size and parameters. We look at the shelf length. We get an idea how to put the stuff together, and find the screws. And now I get gyro to hold this in the right position so that we can put it together. You know, if it's on the floor, you can't do it. So, and this is what we do with the molecules. We take the molecules in the computer and with the coordinates and turn it around and then put it there. It's really like putting furniture together. And then we have a spatial alignment and integrating of fragments, and this has something to do with the shape of the connectors. And at the end, we have indeed a molecule. But here you could think the screws are not tightened yet. They are only, you know, put together. And it is not in all cases clear whether we can actually tighten. So we need to now see whether after tightening the screws, this shelf still stands. Okay, so what we do here is then so this process gives us computational ready structures. So we can now import these structures into, say, Gaussian, or we use tight bindings because XTB, because these are large structures, and you want to start with the lowest level of theory. And what you see here is MOPs, and it's described here, and 4 linkers, with 4 linkers, and these are different types of linking, and this is the metal part of that MOP, and this is just the basically acts as an edge, and you then calculate the energy. So this is what you get when you just assemble it, and then you geometry optimize with different level of theory. And for these MOPs, there are XRD measurements, and you can see that if you basically start to tighten the screws, that the shelf more and more looks like the thing you see in the catalog, okay? Right? So this is what's happening here, and here another one. It is also clear, so here is the untightened representation, just by playing Lego, nothing else. In my view, it's already very good to be so close to the real value just by geometric arguments and symmetry arguments, because that is what really is behind all of this. And this is another example of a linker. Here we do not have measurements. Right, so this is the geometry optimization. Here, this gives you what you can then do. You can calculate the radius of duration, and you'll see that you have to also include solvent effects, and we did this with a Cosmo model. And this gives you roughly the uncertainty of, in this case, radius of duration. So it's still reasonable. It's reasonable, but it's not super exact. You know, a hardcore theoretical chemist would probably get a heart attack, but it's not too bad either. So, and then the next thing is, you want to check, it's a bit late in the day, but you have just built the shelves, and now, does it fit in my room? You know, of course, something that you should have checked before you actually ordered it from Amazon. But in this case, everything is still in the computer, so it's not so bad. So we look for a MOP, and we have a specific application in mind, for example, CO2 absorption. And then you see, okay, the cavity is not big enough. So, okay, we need to exchange these linkers and just build it bigger. And remember, these linkers, these are part of an occurrence class. We have thousands of linkers. We can just pick something bigger or has better electronic structure properties and so on. Okay, so now we build the big one, and then we look at the energy, and okay, this has actually a lower ground state energy, and that means that we may be able to build it. You know, if it's higher energy, probably not so stable. So we try to pre-select structures that are also in theory stable. Okay, and of course CO2 fits in. Then we also look at the linker exchange reaction energy, and basically look what energy contributions different linkers have, and if they are lower, then that is a preferred linker to pick to help pick the right ones. So now we have decided on the molecule. We have at least in our head put the shelf into the room. But then we actually, this was all imagined, but now we have to actually do it, okay? So in chemistry, there is not a little man who puts these molecules together, so you have to use some wet chemistry and so on. And I have to admit that I've never done wet chemistry myself. My sister did this. My sister studied chemistry, And therefore, as a little brother, could not study chemistry. That was not on, okay? Because my sister was always the one who did everything perfect. And I wasn't quite as perfect as my sister. So I thought, I don't want to hear, yeah, do as your sister do. So I studied mathematics instead. And it turned out it was a good choice because you don't have to learn as much. You know, that not in chemistry is terrible. What they have to learn, the number of molecules and names, terrible. So anyway, now here I am trying to do synthetic chemistry. So how do we do this? Okay, obviously I cannot do it from memory because I never done it myself. Okay, so you go and try to get it out of papers, and this is where these generative large language models kick in, because you then just, I told you already, we have 100 and basically 150 papers, and they all have a synthesis part. So you want to extract it, and of course you need to formalize it. You need to pull these recipes out, okay? And we did this with a combination of large language model and world avatar and switch back and forth. And this is sort of the classical keywords are chain of thought prompting, structured output, in-context learning, and RAG, also retrieval augmentation. And that basically means nothing else but going to the world avatar, taking information, combine this with the prompt, run the first prompt, do it again, run a second prompt, form a few examples, do it again, check whether it's correct, and carry on. And then at the end, you end up with the recipe, okay? And in order to be able to have a formal representation, you need to define an ontology. And here you see a little bit, you have a material, chemical transformation, chemical synthesis, a synthesis step, has a vessel environment, has a duration, has a yield, and so on. Now you formalize the synthesis representation, and we call this ontosynthesis, our first attempt. I'm sure it's not perfect. And this connects, and now you see the beauty, this connects directly to our species representation. So, for example, a species has elemental analysis, has an NMR spectra, spectral information, and so on. And then finally, we basically borrowed Lee Cronin's description and turned that into ontology and basically come up with some sort of unit operation, dissolve, separate, transfer, evaporate, dry, blah, blah, blah. So anyway, we've done this. And then you fill this in your prompts, and then I won't explain this in detail, so don't worry. So we have 7 prompts that then pulls this out of the literature, and we end up with a recipe in formal language, okay? So now, this is just maybe a short comment. We have to, of course, integrate it with existing knowledge, and there are basically 3 things that sort of are relevant. And one is a unique instance upload. So for a new scalar, you get values, because now imagine you have, so we know you have to stir in a beaker for so many minutes. And of course, if you have a different material, it's not 5 minutes, it's 10. And then you have to update it, and you have so much solvent, and that also needs to be updated. Then you have predefined entity linking. That means we now use, in order to prompt, we need to give examples in the prompt of a formal representation of a synthesis procedure, so that the large language model can then sort of compare what is in this text. And that is what we call predefined entity linking. So we know a synthesis step has a vessel environment, and then we can add these new features from the literature. And finally, we have to pull information across different representation of the knowledge graph, because although I talk about as if everything was one, from a technological perspective, we have a stack, and information is distributed over different stack. So you have to do federated queries and so on. Anyway, so these are aspects, and now you can look at the data analysis, and you see that metals fall in sort of different areas of heating temperature. So for the synthesis prediction, we say we apply the same heating, and then we use analog reasoning. So we say we want to have a mob that has a metal and a certain linker. Okay, we call this M0 and 2. And we don't know the assembly model, and I'm running out of time. So, but the point here is that we use reasoning and analogy to come up with potential. Here, this list is a list of things that have similarity, and then we create a similarity measure. You will see this in a minute. I won't go into the, you see here, the important bit here is this. You have a similarity measure, and that is then what you do for structures that we have suggested and imagined, but we don't have the recipe on how to cook it. So we are now basically, by analog reasoning, get the new recipe for structures that have never been reported. Not only we identified it, we were also able, because of the representation, we are also able to come up with a recipe. Okay, and just to show you, this is how to find out how much stuff you should take. So we checked this. So we took one of the, this is sort of a test set. We took a structure from literature, run it through our process, and see what our analog reasoning came up with. And so the green means super, means it's identical, and blue means it's close, and red is a bit different. So so we used our recipe, and we did some powder XRD, and were able to see some similarity. And then we moved on to unreported structures. So these structures have not been found in the literature, and created the recipe for that. And here you see powder XRD, and we have a different score. And when if you take mass spectrometry, you see that we formed with the recipe, two of these structures. So we are at the moment still trying to specify this in more detail. And I'm now at the end of the talk. You're very brave sitting through it. Okay. Bottom line, what I basically showed an approach to approach an interoperability problem. I sort of claimed that knowledge engineering is the way forward, and introduced my baby, the world avatar. This open is not my thing. It's an idea more than anything else, a way of thinking. Everything we do is in the public domain. I showed then an example, reticular chemistry, and basically demonstrated that with explicit knowledge representation, it's an alternative to just machine learning to find new materials. And with that, I would like to end my talk, and thank you very much for listening.